Ave Coders. It's time for some necessary theory before we'll begin building our models, so you will at least have an understanding of what is going on. Of course, topics covered here are vast by themselves and most likely will only be able to scratch the surface, but this should be enough for a good start in machine learning. In this lesson, we'll touch on the problem of overfitting and underfitting that our models are exposed to. Therefore, we need to understand what we are really looking for in terms of our model's performance. In particular, we'll talk about something that is called the Bias Variance Tradeoff. In short, this is similar to getting the most on one side without losing too much on the other. I will try to keep slides as simple as possible and explanations as easy to grasp as possible. Therefore, I will use some unconventional analogies, but rest assured, they work. In fact, the more bizarre the analogy is, the greater is the chance that you will remember it and therefore the underlying subject as well. For example, what can you see here? A raccoon? And I can see that you haven't subscribed to this channel yet, you see? For instance, let's talk about darts, but not the modern one, rather its Old Norse version. Imagine that we are Vikings. We just returned from a very stressful voyage and straight we went to the local pub where we can relax, enjoy ourselves and play some pub games like throwing axes at this board. So the evening just began and our board looks like this. We have low bias and low variance. Then after a few pints our board looks like this. Here we have a low bias and high variance. That is, overall we throw in the right direction, but we can't hit the target so accurately. It's getting late and our results are not the best, as we see that now we have high bias and high variance. So we decide it's time to take a nap, so we fall under the table and snore. Our place is taken by a sober but slightly cross-eyed Olaf. His hand is firm, his variance is low, but he is constantly off the target. Putting this into the context of machine learning, we can say that bias is the tendency of an algorithm to constantly learn incorrectly, for example, without taking into account the entire set of data. Thus, the high bias may appear as a result of the algorithm missing the necessary relationships between features and target outputs. In essence, our model does not fully understand what we're trying to achieve, and so its results are consistently shifted to one or another direction, or in other words, they are biased. Variance, on the other hand, can be described as the degree of sensitivity of our algorithm to fluctuations in the training data. The high variance may be the result of applying the algorithm to arbitrary noise in the training data. It is possible that our model was overtrained on the data it has already seen, perhaps even just memorized everything, and therefore can be almost 100% certain when classifying the data it is familiar with, but get confused when it sees the data that it has never seen before. Let's plot it on a graph. Here, the x-axis is the complexity of the model, and the y-axis is the error. The red line depicts our bias term. You can see that it declines with the increase in model's complexity, but that part of the graph where it remains high generally indicates that our model is undertrained. The green line depicts our variance term, and since it reflects the sensitivity of the model to fluctuations in the values of the input data, its increase with model complexity might indicate that the model was overtrained. And thus a compromise arises called the Bias Variance Tradeoff. Therefore, as with everything in life, we have to find the optimal balance in order to reduce what is shown by the blue line, the total error. For those who are just listening to this video as a podcast and can't appreciate the charm of my drawings, I will summarize this with a formula. The total error is the bias plus the variance, and plus the so-called irreducible error. That is a certain amount of error that the model will never get rid of. Because like with any compromise, 100% success in anything is a pipe dream that can never be achieved. But in order to understand how we can achieve the optimal balance, we need to consider two concepts, underfitting and overfitting, that will directly correspond to the model being undertrained and overtrained, respectively. Underfitting is the termination of the training process of an analytical trainable model before it reaches the state that will provide a sufficiently small error on the training set. In other words, the algorithm is unable to reflect on the trends in data. If we apply this to the Titanic problem, that is a problem of classification, then something like this will look like a fair attempt to draw a straight line between survivors and those who are not so lucky. Let's say the x-axis represents passengers' age and the y-axis represents ticket price. Survivors are depicted with nulls and non-survivors are depicted with x's. So to summarize, this plot displays how we classify passengers as survivors and non-survivors based on their age and the price of their tickets. Our line, otherwise called the decision boundary, is drawn quite clumsy. In fact, it could separate those categories more accurately if it would have had curves. But it shouldn't be too curved, because we don't want to fall into the other extreme called overfitting. In other words, a model overfitting is observed when the model shows good results on the training set, but drastically bad results on the unseen data, for instance, coming from the test set. This graph depicts two extremes. On the left, we have high bias and low variance, and on the right, we have low variance and high bias. And our goal is to find a balance or a compromise between the two. Ideally, we would want our model to have low bias and low variance. In terms of our classification problem, we want to find a decision boundary such that it effectively separates one class of data from the other, but at the same time not too precise so that the model would be able to generalize on the unseen data. In other words, when we'll finish training it on the training set, we want it to recognize patterns and draw a good demarcation line when we'll show it the test data. We can try to summarize this in the following table, where the optimal model can be depicted as quite complex, but not as complex as the overfitted model. Here is the question: how do we establish that our model is overfitting or underfitting? This plot depicts the total error that we can observe on training and test sets relative to the model's complexity. Let's imagine that on the left we have a very simple underfitting model, and on the right we have an overfitting and very complex model. And between them there is a good model of medium complexity. And as this plot shows, the underfitting model suffers from the high error on both the training and the test data. The ideal model in the middle has a low error on both types of data, and the overfitting model suffers from the high error on the test data but a relatively low error on the training data. Let's add our findings to this table. Usually, if we want to understand how our model is doing, we would observe the results of its performance on the test set first. If the error is low, then it might be a good indicator that we have a good model. However, if the error is high, then we want to look at the model's performance on the training set. If the error on the training data is minimal, then we have a model that is overfitting. But if the error is high, then most likely we have an underfitting model. In the next lesson, we'll continue with the necessary theory and we'll look at hyperparameter tuning and regularization. That later we would be able to apply this knowledge to practice, building a pipeline from start to finish. That was V. Please give this video Emperor's thumbs up, toll the bell and subscribe. Thank you, and I'll see you in the next lesson. Cheerio.